All right. As I promised, this is going to be a little quick video going over all the reactions. I'm going to post this PDF to Learning Suite with the video. That way you guys can have access to it to study, do whatever you want. Yeah, I'm just going to jump right in. I'm not going through everything in the study guide. I might make a video about that later if you guys request it specifically. Send me an email or something. Otherwise, Josh will have his review in person that will have the majority of the rest of the content for this test. This is going to be specifically just reactions, specifics you want to know about the reactions, not all of the stuff that you need to know, such as like alkene stability, I don't know, some of the other stuff that's probably in there. Haven't looked at it yet. All right. Starting off with elimination reactions. This is really crucial to know just in general for all of chemistry, organic chemistry, biochemistry, chemical engineering, I assume, whatever way you're going. So make sure you have E1, E2 down. With E1 specifically, also for the formatting of this, I already wrote out all the reactions so I don't take an hour and a half of your guys' time just trying to come up with different reactions or like different reagents. So I just wrote them all before just to make it easy for y'all. All right, so E1, it favors high temperature. Delta S will always be greater than 0 because there's going to be more products than reactants. It is a polar protic reactant, it reacts fastest with polar protic solvents. And it is best with a weak base. And one thing that's really important that a lot of you guys missed on the recitation sheet, when there's an E1 reaction, there's also an SN2 reaction. Why, you may ask? Well, because both E1 and SN1 use a weak base and a polar protic. In SN1 reactions, we say a weak nucleophile, which is very similar to a weak base. This is a weak nucleophile and a weak base. Also, often the solvent is the base as well in the reaction. So in this case, this is the solvent as well as the base. And also, another reason it occurs with SN1 is because it goes through carbocation intermediate, the same exact carbocation intermediate that happens in SN1 reactions. Something essential that a lot of you guys also missed with the recitation sheet is that every time there's a carbocation intermediate, regardless of it's an elimination reaction, E1, SN1, any other type of reaction like addition, any reaction that has a carbocation intermediate, check for methyl shifts, hydride shifts, because anytime there's a carbocation intermediate, it can happen. So every single time, look for that. Rate determining step will be the first step of the leaving group coming off. And you can see that right here. Rate determining step is the rate law is K times the alkane or the organic reagent. And then it goes through the carbocation shift right here. And as you can see right here, there is a methyl shift. Typically, methyl shifts only happen when there's a secondary carbocation next to a quaternary carbon. This has 4 different things. So typically, it only happens when it's like that. There's not really primary carbocations due to, I don't know, that just doesn't happen for E1 or SN1. Yeah, so that's when methyl shifts happen. Hydride shifts are more flexible. Just move the hydride, and if it's a more substituted carbocation, then it's going to be favored. And then with E1 reactions, you look at all beta carbons. Beta carbons are the carbon directly next to the carbocation. And then all the hydrogens attached to the beta carbon, or these are also called beta hydrogens. And you can eliminate any of those hydrogens. So you could come in through this side, attack this hydrogen. This is also a beta carbon, but it's the exact same thing as if you took off this one. And then you also can do this one. What is going to happen with E1 is the most stable formed alkene will always be the major product. As you can see, this is less stable because it's a less substituted alkene. This is a tertiary substituted, or whatever it's called. There's 4 substituents off of this double bond, so it's more stable than this. This is the major. E2 reactants, or reactions. E2 reactions favor a higher temperature. And I'm going to write this in there. Up here. Ooh, what is it? Delta H minus T delta S. So you know that this is positive. Delta S is greater than 0, which means that as you increase temperature, delta G will be more negative. And that's why elimination reactions will favor higher temperatures over substitution. So if you want to push an E1, SN1 reaction farther towards E1, increase the temperature. All right, elimination, or E2 favors a higher temperature, the same, delta S the same. Polar aprotic solvents, though. Same with SN2, it's polar aprotic. E2 is polar aprotic. One distinguishing thing, though, is E2 does not happen with SN2. You can have either or. It doesn't typically happen together like it does with E1, SN1. You need a stronger base, whether that's bulky, like this is terpetoxide, or a small one. It just needs to be strong, so typically negatively charged. And the chloride leaving group and the hydrogen that will be attacked in the acid-base reaction need to be anti-periplanar to each other. This is the example I gave, where you have the chloride right here. I drew it right here, down here as well, where it's up, so I put it as axial. And then the hydrogen next to it will be down. Or over here, this hydrogen. And as you can see, if you look at this from this carbon, ooh, why is my pen so fat? No, it's too skinny. All right. I'm going to do a different color. My bad. That's just not going to be very clear. Purple. So that is this right here. If you're looking down this structure in a Newman projection from this carbon to this carbon, you'll have this right here, this Newman projection. And as you can see, the chlorine and the hydrogen that you eliminate with this OCH3, they are anti-periplanar, which means they're in the same plane but opposite from each other. So that means it can be eliminated. When it's a ring like this, it needs to be, the 2 substituents also need to be axial. So like chlorine is axial, hydrogen is axial, this hydrogen is axial, so you could eliminate either this or this side. This beta hydrogen or this beta hydrogen. I'll highlight those beta hydrogens again, just to make it a little bit more consistent. Beta hydrogen, beta hydrogen. You can eliminate either of those. Beta carbon, beta carbon. All right, so with a bulky base, or a large, strong base, such as terpetoxide, that's probably the most common one that you'll see. You'll come in, and because of all the steric hindrance in this big old group right here, you can't come in to this hydrogen because there's too much going on right here. It won't be able to come in because of the steric hindrance. So it's going to do an acid-base reaction with the most accessible beta hydrogen, which is this one, because there's less steric hindrance, and it's going to form the kinetic or Hofmann product. And this is, as you can see, it's not the most stable product, but it will be the major product because it's a bulky base attacking the least sterically hindered hydrogen. With a small, strong base, it'll do whatever is most stable and attack the hydrogen that will result in the product being more substituted. So that is called the Zaitsev product. Thermodynamic, small, strong base, kinetic, sterically hindered strong bases. I think that is everything for elimination. Also, rates, something important to note. Both E1 and E2 are fastest with the tertiary. I think E2 is always faster for the most part because you don't go through a carbocation. But E1 is impossible with primary. All right, alcohols. Moving on. Let me find this. Cool. Alcohol prep is pretty basic. It's basically a substitution reaction. SM1, SM2, I guess it could be both. Where you have an NaOH to get the hydroxide group attacking that carbon coming off, alcohol. Simple enough. I think this will typically be in water, H2O, and I think it's going to be like equilibrium basically. I think you learned this in Chem 106, where it's H2O is in equilibrium with the OH minus and the H plus, but the OH minus is just in a higher concentration, like a very high concentration. William ether synthesis and sulfides. Same exact thing, substitution reaction. Instead of a hydroxide, use whatever that thing's called. And you form the ether, where the R can be any carbon group. Acid catalyzed dehydration. Cool. All right, you need a strong acid for this. That's important to know. And I don't know if it really matters if you include this step in this mechanism, but I think realistically what would most likely happen is the H2O would deprotonate the acid before this alcohol group would. And it would form this, and then the alcohol group would come in here and deprotonate that. And anytime that alcohol deprotonates an acid and becomes this positively charged hydroxide, it's going to be, it looks a lot like water, which means it's a good leaving group. One of my OChem professors did that really hard. First thing that happens with an alcohol and a strong acid is the alcohol is going to be deprotonated, and if it looks a lot like water, it's a leaving group. Cool. And as I said before, there is a carbocation, so you always have to look for carbon shifts, methyl shifts, or hydride shifts. In this case, there is a hydride shift because this carbocation is much more stable than this. Tertiary, secondary. And then from there, you can attack from all of the beta carbons or beta hydrogens, same as a regular E1 reaction. And you're going to form the most substituted product. Something important to note, because E1 carbocations cannot shift with primary alcohols, or primary carbocations do not form. So that will happen through E2 even with the acid catalyzed dehydration. E1 will happen with the secondary and tertiary. Cool. Pockle. This one is just a mechanism. You guys have to memorize it. I drew out the whole mechanism. Alcohol attacks the phosphorus. Those electrons come up here onto the oxygen, and then those electrons come back down, collapse this intermediate, and knock that chlorine off. Then the pyridine, depicted right there, will come in as the base, pull off that hydrogen, and then pyridine will come in again and pull off that hydrogen and form your product. In this case, the most stable product is going to be the major product. And the antiperiplanar requirement is still in force because it's E2. An E2 elimination, this is always a requirement. So if I drew stereochemistry right here, they'd both have to be axial or opposite to each other. All right. What is this? I guess this is alcohol substitution with a strong acid. So in this case, it's going to be very similar to what we just did. And yeah, so the alcohol is going to deprotonate the acid. And just a side note, HBr, HCl, you don't have just 100% HBr, HCl. Those will always be in like an aqueous solution. But yeah, this is just basically another substitution reaction where you make water a good leaving group, or the alcohol a good leaving group by protonating it. Looks a lot like water, so it's going to leave. Something important to note, SN1 is the mechanism with tertiary alcohols, SN2 with primary alcohols. This is a secondary alcohol, and it can be SN1 or SN2. I think it's based on those conditions you learned for the last test. But something that is crucial is that if it is SN1, you have to look for the rearrangement. Or if you're working backwards, if you notice there is a rearrangement, that means that it goes through SN1. And that might be the question where it gives you the product and it asks you if it went through SN1, SN2, and if there's a rearrangement, it's SN1. All right, Sockle, SOCl2, and crudine. Sockle, one more thing you can remember, S, so it's substitution every time. And this is going to happen the same way. The alcohol is going to attack the S, the sulfur, knock it up onto the oxygen. It happens very similar to Pockle. It just goes through substitution instead of elimination. And then it makes this alcohol a good leaving group when it looks like that. And then that chlorine that gets knocked off in this step comes in a nucleophilic attack and attacks that and knocks it off in an SN2 type reaction. And there's inversion of stereochemistry. That's important to remember. And it's best for primary and secondary carbons or alcohols. Wow. Best for primary and secondary. This is a secondary. So it's best for those because SN2, it happens through SN2. So there's no rearrangements, which makes it so you can predict the product really well. So if you're actually doing a synthesis of a chemical, you're not going to want a bunch of carbocation shifts because they're unpredictable. So people tend to gravitate towards Sockle or a product that does, or a reactant that does something similar. Tosylates. You do not need to know the mechanism for this. Just know that the TSCl, it happens basically the same as all this. But O comes in, attacks it, and then knocks the Cl off, and then you got OTS, which is great because it's a leaving group, and you can either do elimination or substitution. So this basically converts OH to a leaving group. And with this one, you can do either elimination or substitution. It's not like Sockle-Pockle where they're specific. Acid catalyzed ether cleavage. We talked about this one briefly. I don't think I was here for this one, but I vaguely remember this on the test. I think it was actually a tricky one because it was something we hadn't seen a lot, where it was like a ring ether. So it's going to happen exactly the same way. So if there is a trick question like this where you haven't seen it before, just think for a long time about what you do know, and chances are it's going to apply in the same way. and basically do the exact same thing with like a slight twist. And that's exactly what happens here. Anytime you're breaking open a ring like this though, I want you all to number the carbons, because it's really easy to lose track of or add or delete a carbon when you're extending a ring like this into a skeletal structure like this. So same exact thing happens. Oxygen attacks the acid, leaves iodine. Iodine comes in, nucleophilic attack, knocks that off. And because the HI is in excess, it's going to happen again, where the alcohol is protonated, and then the iodine comes in for a nucleophilic attack and forms that diodo something. I did another example right here, and in this case, if I'm going to be 100% honest, I don't know if the iodine is going to attack this side or this side. I know Professor Stowers checked all of these mechanisms that I drew out, and she said they all look good. So chances are this is right. I just don't know if it attacks the less substituted or the more substituted carbon. But she said that they look good, so chances are this is right. If you really, really are worried about it, you can look it up, just to double check you're right. I tried to look it up and I couldn't find anything like super clear. But in the end, I don't think it matters that much because once again, we'll act like this is excess. I'll say it's excess right here. Oh. And then, like I said before, acids like this are always aqueous. It's never just an acid. Same exact thing as the mechanism above, where there's the first round where it's those two products, and then the alcohol gets deprotonated or deprotonates the acid and then makes it into a good leaving group. Looks a lot like water. Iodine comes in and then nucleophilic attack and forms the second product. Epoxides. Trying to get through this really fast so you guys don't have a super long video to watch. It's probably going to be most effective just to read through these, really have them down, really have them memorized. Hopefully not just memorized, hopefully you understand the conceptual stuff as well. All right, epoxides. In basic conditions, just as with like a bulky base, even though this isn't a bulky base, here's a negative charge on this. It's going to come in, attack the less substituted side, and invert the stereochemistry, and form this. Yeah. With acidic conditions, the first thing that happens, like I said before, first thing that happens when there's an oxygen in really acidic environment is the oxygen is going to deprotonate the acid. And then because this is a positively charged species right here, it's going to push away from the group with more steric hindrance. So something I like to think about is like, it's almost like the transition state. I think it said this in the textbook, where this side is already like started breaking almost, while this side is shorter. Okay, that's terrible. I'm going to redraw that because that might be important. So because there's a positive charge, it's going to push away from the more sterically hindered side. And then because of that, this bond right here is already weakened, and then you're going to have your acid, weak nucleophile, come in and attack through that side because this bond is already breaking a little bit. Because this is just not a stable thing right here. All right, and then it's going to invert stereochemistry in the exact same way. And then that's going to be deprotonated through the solvent. Alkenes. Prepare through elimination. Enough said. Alkynes. It's double elimination. You just need a strong base. And you can use NaNH2 or NaH. these both dissociate to NH2 minus, Na plus, Na plus, H minus. And for these double eliminations to synthesize alkenes, or alkynes, is that spelled wrong? No. The NH2 is just going to work the exact same way as regular elimination. This will just be the strong base. SN2 or E2 elimination, where it forms this double bond, and then it's just going to happen again. Form the triple bond. Cool. I really like NaH because in this reaction right here, where it comes in and attacks that, it's going to form H2, which is a gas, and then it bubbles out a solvent, and then like it's just, you don't have to worry about it. So in real synthesis, that's like comes in clutch. All right, moving on. Hydrohalogenation. Which chapter is this? I'm trying to follow along. This is chapter 10 and 11. Just so I can let you guys know where we are. All right. Hydrohalogenation. So with this, you're going to need a strong acid, and it's going to deprotonate that acid, or the double bond is going to act like a nucleophile and attack this, which is the electrophile. And then it's going to form a carbocation, which will always be on the more substituted carbocation. So you have this possible carbocation and this possible carbocation as seen right here. This leads to a secondary carbocation right here. This one's a tertiary. So this does not happen, but this does. And that's called Markovnikov's rule. Is that spelled right? Yeah, I assume it is. Where the Br will go to the more substituted carbon. And because there is a carbocation intermediate, this bromine could attack from the top or the bottom, and it will lead to an enantiomeric mix of products. Here is a double hydrohalogenation. And the same exact thing is actually going to happen. Markovnikov's rule, where the carbocation forms on the more substituted carbon, and then the bromine will come in and attack that, and it's going to happen twice in the same way. So the bromines will end up on the same carbon and end up with a product like that. If you don't know exactly, a couple of times some people have asked me about this one, why the bromines end up on the same carbon and not on like the opposite carbon, because that would be like a more stable product. Because there's a lot of steric hindrance here probably. If you don't understand anything on the test, or like you're a little bit unsure, just try to draw out the mechanism, and oftentimes it comes out to be pretty logical. Chemistry for the most part is pretty logical. All right, halogenation. Where you have a dibromide or a dihalogen. This is just a possible solvent. I'm probably going to write down all the solvents. I emailed her and asked her, or Professor Stowers, about which solvents would be good to know. And she sent me a list, and I'm going to write them down at the end of this. I just haven't done it yet, forgot. But that's besides the point. So halogenation, this is kind of confusing. First thing that happens, double bond acts as like a nucleophile and attacks that. And then you're going to have another bond, this bond come over here, and then this will be a neutral species, and it's going to come in and attack that and form this positively charged bromine. So it's going to be like all concerted though, kind of like this circle with that, and then this is going to come off. And this is going to form this. And then this bromine right here is associated with this bromine. And then the bromine will come in and attack. I believe it usually attacks the least substituted side, but if I'm going to be real, it doesn't matter that much because both sides are going to have a bromine. And it's always going to do anti-addition, which makes sense because as this bromine comes in and attacks this, it's going to add opposite stereochemical configuration. So we got that and that. And one thing that's important to note, this is flat. This bond is flat. So it can attack and add that bromine either through the top, like I wrote right here, or it can come and do this side. And then this bromine is going to attack that one side. So it's going to form enantiomers. If you do it across a triple bond, it's going to basically do this the same exact mechanism, but it's just going to do it twice. Cool. Hydration, acid catalyzed. All right, so typically first thing that happens, H2OSO4, strong acid and a solvent, is this one will definitely happen like this because the alkene is way less acidic than a water group. So the water group is going to deprotonate the acid to start, and I drew that right here actually. And then the alkene is going to come in and attack the protonated water. And then you're going to have kind of the same thing as what was happening right here, where instead of having bromine as your nucleophile or a halogen, you're going to have water as your nucleophile. This is a carbocation intermediate. It can come in through the bottom or top, which will lead to an enantiomers of each other, as you can see right there. And yeah, not much more to say about that. What is this one called? This is also, I think it's just called hydration, but it's of a triple bond. So for this one specifically, you need this mercury reagent as well. Her reasoning was if it's not in there, it will form tar, some tar-like alkyne stuff. So same thing's going to happen right here. Water is going to acid-base reaction with the acid, and then this alkyne is going to come in, deprotonate this, and the carbocation is going to form on the more substituted side right here. And then from there, you're going to get water addition to the carbocation, which will, I skipped a step right here. My bad. I'm going to just fix it real quick. I'm going to draw small so I can fit it in there, but too small. Too big. There we go. So then you're going to get water that deprotonates this. Yeah, that looks super janky. Cool. Good enough. And then you get that deprotonation, which will lead to this enol. This is called an enol, this type of structure, where there's a double bond next to an alcohol. And enols are not super stable, and because of that, they will always go through tautomerization, which will lead to the keto form. So these are tautomers of each other, the enol and the keto form. They're tautomers. And something important, when you do this, you don't need to know the mechanism. It's kind of complex. I mean, it's not too complex, but it is just extra stuff you don't need to know. It's either acid. Wow. Whew. forget that. Acid catalyze or base catalyze. But you just need to write that it happens proton transfer through the solvent. It's not actually going to be this proton moving over to there. It's just a proton transfer through the solvent. Make sure to write that so you get full points. Oh, I'm tired. Almost done, I think. Let me see. Okay, well, almost is a stretch. You guys have a lot to learn. All right, hydroboration oxidation. This one is relatively simple. It's across an alkene. Write it out like the H is separated from the BH2. So separate one of the H's. And then you can just have the H, or the double bond attacking the B, which goes over to here, forms this hydride ion, which attacks that. And it all is concerted. So this is like the transition state. It's kind of like that concerted thing that she talked about a lot. And one thing that's important to note, this is stepwise. This is the first thing you'd add. And then after that's done, you add this. But yeah, the important thing to know about that is that the BH2, due to steric hindrance, will be on the less substituted side of things. You don't want the BH2 binding to this or bonding to that because there's more steric hindrance. So it pushes it to that. And then through a bunch of other stuff, the mechanism is actually kind of terrible. You're going to get anti-Markovnikov addition because the bigger group is adding to the least substituted carbon. And yeah, I think that's all you really need to know about that. The same thing happens as up here with an alkyne. Same exact thing where the BH2 will be on the less substituted side and form this transition state, form this after complex mechanism. I skipped this. I should have written that, but I didn't. I was tired. I'm still tired. And then you're going to get tautomerization. Proton transfer through solvent is what you need to write. And you're going to get this. This is the enol. This is the aldehyde. All right, trans addition. Wait, no, that's not trans addition. What is this? Oh, yeah. This is acetylides. Whoa. All right. With this, you need a strong base. NaH, NH2 will do. I like using H, as I said before, because it deprotonates that, turns it into a gas, and leaves the solvent. And then it's going to deprotonate this, form a super strong nucleophile, which will basically do everything that a strong nucleophile will do. Substitution, potentially elimination, I think. Probably substitution. That's going to be the most useful. And it's really useful in synthesis if you want to extend your carbon chain, because once you have this, you could just hydrogenate it through catalytic hydrogenation. What is important to know through this? This is done through like a metal catalyst. It's like a metal surface. You guys should be able to know how to draw this, like kind of. At least know the idea, and you should be fine. Where there's like this metal catalyst, which is either PDC, NIC, or PTC. The hydrogen kind of bonds to it, and then the double bond or triple bond binds to that, and then adds those hydrogens. And because it happens like this, the hydrogens will always add syn to each other. So there's syn addition on the same side. With these reagents and H2, you can also do this to a carbonyl. Once again, syn addition. It basically reduces everything. Then we get to the poison catalyst, which is Lindlar's catalyst, which is this. You should know this, I think. This is important to know. This is Lindlar's catalyst. And what Lindlar's catalyst does is, with an alkyne, it starts to... Oh, starts to reduce it, but then it stops at the alkene. And because it's syn addition, it's going to stop with the cis alkene, because you can think of the hydrogens being added like that, syn to each other or cis to each other. So it's going to stop at the alkene. With the carbonyl, it's not going to do much. All right, reduction to trans-alkene with NaNH3 from an alkyne. You're going to use the NaNH3 as a solvent. And this Na is going to dissociate into the cation and the free electron, which will come in and do a radical attack. I don't know if you guys talked about this, but typically when you're doing this type of mechanism with one electron, not a pair, you draw your arrow like this with half an arrow. And it's going to attack one of the carbons, and then that is going to, both of those electrons are going to come and do that. So now this is the more negatively charged side, and it's going to come over here, deprotonate your solvent. And this, after it's deprotonated, typically NH2 is incredibly unstable. It's a really, really strong base, so you don't really want that. But because you have this this sodium cation right here, it's going to form a complex right there and stabilize it a lot. And it's going to form this trans because the steric hindrance between this carbon and this carbon, they're going to push each other away. And those are the biggest groups. The electrons have something to do with it, but this is the main reason. I looked it up. All right, then the other electron's going to come in, attack that radical, form an electron pair, and that's going to happen again and form this. Carbonyl reduction. I didn't write down any of the products. All right, let's see if I remember this. I don't know if I do. All right, well, NABH4, this is weaker, and this is a super strong reducing agent. With a ketone, NABH4 is strong enough to reduce that. And a reduction basically means that the carbon-hydrogen bonds are increasing, carbon-oxygen bonds are decreasing. Yeah, so this is reduced. Oxidized is the opposite. Yeah, I think that's fine. That's good enough to know. And then with an aldehyde, it is strong enough to reduce that to a terminal alcohol. And then with an ester, I misdrew that. NABH4 will not do anything. It's too weak. LAH is a common name for lithium aluminum hydride. Oops. It will reduce this, obviously. It will obviously reduce this. And if I remember right, it's going to reduce this into two separate groups. Oh. Yeah, I think that's good. I need to number the carbons. So there's only 4 important carbons. Yep, so it's going to reduce into that. LAH will also reduce halogens, basically replace it with a hydride. And it's going to open the epoxides. You can think of the H coming in and attacking this side, breaking it open, and then H2O is like a workup step to protonate this. They are in separate steps, that's important. You don't need to know the mechanism for all these in this test. I'm pretty sure you do need to know it for next test. So it doesn't hurt to know it and learn it right now. But you can just remember that all of these basically are an H- ion coming in and performing nucleophilic attacks. We are almost done. Oxidation. You do need to know this or the mechanisms for these for this test. So we got two reagents or types of reagents that are most typical. You got this, I forgot what it's called, but CrO3, and then this bigger one. These act the same. And these are strong oxidizers. And then you got PCC, which is a weak oxidizer. The strong oxidizer is going to basically oxidize everything all the way. So with a primary alcohol, it's going to oxidize it always to, all the way to a carboxylic acid. And you're going to want that acid workup in there. With a secondary alcohol, it's going to make a ketone. And with a tertiary alcohol, nothing happens. And that's universal for the strong oxidizers as well as the weak oxidizers. Nothing happens because you'd have to break a carbon-carbon bond to oxidize it. PCC is the main difference is that with a primary alcohol, it's going to stop at the aldehyde, while the strong oxidizer would go all the way to a carboxylic acid. PCC will then oxidize the secondary alcohol to the ketone just the same as this. All right, so for the mechanism, I think when I look it up, it's a little bit different, but this is the way she taught it. So I assume this is what she wants you to know for this class specifically. I've always learned or thought that this reagent is different. Basically, I've always thought that the chromate and the Na2Cr2O7 react with H2SO4 H2O to form a different thing, and then like both of these will have the same exact reagent, and that's like kind of why they do the exact same thing, is because in the acid they form the same exact reagent. But this is kind of what she wrote down in the notes, so this is what I put. So you will need to know this mechanism where the OH is going to attack the chromate, and oxygen, or those electrons will come up onto the oxygen, and then the base is going to come and pull off that hydrogen, the positively charged oxygen. You can't see that, but those electrons come back down. And then this is going to come and pull off a hydrogen off of the acid. And then H2O is going to come and eliminate or do an elimination reaction to form a double bond right there. And continuing the path of the electrons, it's going to knock this group off, form this, and this. I didn't include an acid workup on here. It's my bad. All right, and then if you're going to go all the way to the carboxylic acid, it's all going to happen again. Well, actually, to start off, you're going to protonate this. As I said, if it's carbonyl, oxygen, it's always going to protonate in a strong acid. And then OH2 is going to come in. There is a positive charge on this. And knock that electron pair up. And then it's going to deprotonate that. And then you're going to have a di-alcohol right there. A diol. Wait, no. That might be it. Yeah, diol. And then from here, You're essentially going to do the exact same thing as you did up here, again, where this would come in and attack that, and do the whole process again. Cool. All right, oxidative cleavage. All right, I'm almost burnt out, but I think I'm almost done. These are pretty simple. You don't need to know the mechanisms because they really are, they look really weird. I threw a curveball at you again because I don't remember if it was this one, but there was some type of ring opening type stuff, I think. But once again, you guys know how to do it. You just need to apply the principles you already know to the unique molecule. Oh, wow. To the unique molecule like this ring. So in oxidative cleavage, you're going to take all the double bonds, break them, or all the alkenes and break them, and basically replace it with an oxygen. So as you can see right here, this is a double bond right here, and then I just put an oxygen right there. Same with this. I put an oxygen right there. And then that formed right here in this part. And then if you do the same thing right here, where this is broken, but then you have an oxygen right there, same thing on this side. If you count the carbons, it's going to look like this. Hopefully that makes sense. Just break all the double bonds, put an oxygen on it. Make sure you count the carbons. All right. So with O3 and an alkyne, it's going to do similar thing. Just going to break it. But instead of just putting one oxygen, you're going to put a carboxylic acid. Right here. And as you can see, there's 6,5 carboxylic acid. 1, 2, 3, 4. 1, 2, 3, 4 carboxylic acid. I would number the carbons, like I already said. If it's a terminal alkyne, you're going to form 1, 2 carboxylic acid, and then this one is going to form a CO2, which is a gas. Last things, epoxidation. I don't remember her talking too much about this. Basically, MCPBA forms epoxide, and it can either form it from the top side or the bottom side. Obviously, these are going to be same stereochemistry, either both going up or both going down. That's a given. And then the dihydroxylation, she briefly talked about this. You don't really need to know how, but all you need to know is there's a syn addition of 2 alcohols, so they're both facing the same way, across an alkene. And it's going to do both. It's going to form them on the top and on the bottom, because this is flat. This is a flat bond, so it can go from the top or the bottom. And you can either use KMNO4 and then H2O, HO minus, or you can do this, the blinding stuff, the osmium, and then do a workup step. These are separate steps for that. You need to remember that. Yeah, but I think that is all. I think you guys are going to do better than you think if you just take the time to make sure you know all these. Just practice them. Write out like random molecules. Write out rings. Write out, I don't know, just come up with some random molecules. And then by memory, be like, oh, I want to do catalytic hydrogenation, but with a poison catalyst. And then just like try to remember this, write it out on your own without looking back at like the reagents, and then see if you can get the right product as well. And then go back, check your work. Just do that over and over again. Try to do it for all of them. You guys are going to do great. It's very doable. It's a lot of information. Like this is actually kind of a crazy amount of information, but you have a long time to study, so you guys have got this. Make sure you start now though. And that's unfortunate for all of you guys who are watching this video the day that you're going to take the test. But for those of you who are going to watch this like a week before you take the test, start studying right now. Good luck. You got this.